So what do we do if the vectors are not perpendicular to each other? For example, Johnny drives 36 kilometers west, 30 degrees south, and then 75 kilometers west. So let's draw it first. Let's draw a little sketch of what's happening. West 30 degrees south is, let's see if we have the right color here. West 30 degrees south is like that. So it's sort of like, there's west, and it's 30 degrees here. So we have 30 degrees here. And the length of that is 36 kilometers. And then from there, 75 kilometers west. So if we want to know the displacement, remember what the displacement is. It's from the beginning to the end, right? We want to know basically, I'll do it in green, the beginning to the end of that journey, what is that total distance? Now, this is a little bit more complicated than the previous questions because we have this angle of 30 degrees in here. All the previous questions, everything was at 90 degrees to each other. It was sort of easy to do it. So the approach for this kind of problem is to turn everything into 90 degrees. So essentially what I mean is turn everything into the x and the y components. Because right now we can't really add this thing. Let me erase this right here. We can't add these together because they're at weird angles. But if we were able to break up this vector into its x and its y components, for example, its y component might look like that, and its x component might look like that. So if we express this vector, and let me do this vector in black as the resultant. So if we express that black vector that we know is 36 kilometers long in terms of its y and its x components, then we could do like we did the previous questions. Just add up the x components, add up the y components, and then you see we have a big right angle triangle here, right? So we could find the angle, we could find this length, we could find this length, and just add them to find that length. And that's essentially the process for all these types of questions, is to break down each vector into its components because we can deal with the x and the y. We can't deal with that 30 degrees. So what this looks like, first of all, I like to break up, well, let's call this delta D1 and let's call this delta D2, just to be a little bit more organized. So we have our two vectors. This is delta D2, this is our delta D1, right? And we'll call the green one delta DT for total. Of course, these are all vectors. I'm just getting lazy with the arrows on top. Yep, there we go. Hard to see, and I'm squeezing in there. So again, we need to find the x and the y components of this delta D1. And to do that, I'm going to draw that vector, delta D1, by itself. I'm going to draw it over here. So this is our vector, delta D1, and so delta D1, and we know the length is 36. We also know, let me write the 36 down here, kilometers, because we want the x and the y components. And what we're given is the angle from west, which is why I drew it like that, right? We're given this west 30 degrees south. So that's the 30 degrees in there, right? And if we want to find these components, it was 2 lessons ago, or 2 videos ago, I should say. But remember, the x component, delta D1x, is just equal to, if we start with the angle coming from the west or east, it's going to be 36 cos 30. Just like the sine, delta D1y, or the y component, I should say, is the sine, 36 sine 30 degrees. So we can find those x and the y components. Let's just quickly do those in the calculator. Oh, if I can find my calculator. 36 cos 30 is 31.18. I'm going to carry some extra significant digits here because when you do these calculations and you've rounded too much within the calculation, you end up with a lot of rounding error at the end. That happens whenever you're dealing with angles. So let's just take a few extra. 31.18, and that's kilometers. And the y component will be, if I just change that to a sine, it's going to be 18. Yep, it's going to be half of the 36. 18 kilometers. All right. So now we know what this length is. We essentially know that this length, I'm going to label it on here just because we can, 31.18 kilometers. And we know that that length, the red length, is 18. So just like we did in the previous questions, we can add up our x components and we can add up our y components. So this vector essentially delta D1 can be expressed as the x component being, ooh, I forgot something. Do you notice what I forgot? I forgot the negatives. We didn't actually define what our negative and positive directions are. So we'll call this positive x and we'll call that positive y as always. And if that's the case, both the x and the y are negative here because x goes to the left, y goes down. So anyways, our delta D1 we can express as having an x component of negative 31.18 and a y component of negative 18. And these are both kilometers. Our delta D2, if we wrote the components of that, well, it's only got an x component, and that's negative 75 kilometers. The y component is 0. So now if we want to find our delta dt, it's going to be the total of the x and the y components. So essentially we're just going to add them, right? Negative 31.18 and negative 18 plus negative 75, 0. And if we add those, we get negative 31.18 minus 75 is negative 106.18. And the y component is just negative 18. So remember, what we found here is we found this total x component of the whole vector is this, and the total y component is this. So this essentially describes this final triangle. So the last thing I like to do before, in order to find the answer, is I like to draw that triangle separately, sort of off to the side. I know we're running out of space here, but essentially that triangle has an x component of negative 106.18, so I'm just going to call it 106.18 because it's just a length now, and negative 18, so just, nope, again, I'm not going to do the negative, just 18. And our green one goes down like that. So to find the length, we need to find the length and essentially the theta, the angle, right, in order to describe our vector. So in order to do that, we know this is a right angle here, so we know that, let me just get the pen again, we know that, what do we call it, delta dt, the length of it is equal to the square root of 18 squared plus 106.18 squared, and if we do that, square root of 18 squared plus 106.18 squared is 107.69, and we'll round to how many significant digits? Well, one thing, we're basically adding two things here. So what we're more concerned about is not the number of significant digits, but the number of decimal places, right? So the decimal, it's basically rounded to the nearest whole number. So let's round our answer to the nearest whole number. So 108, about 108. 108 kilometers. And our theta, our angle, again, it's just opposite over adjacent, so it's just inverse 10 of 18 over 106.18, which gives us 18 divided by 106.18, gives us 9.62. We'll just do two significant digits there, 9.6 degrees. So our final answer is that the total displacement is 108 kilometers. And if we think about the direction, it's going west and then a little bit south, right? So it's west 9.6 degrees south. There we go. A lot of work. Hopefully you're able to fit it all on the page. But that is our total displacement. So, and just to check, by the way, does this make sense? Does it make sense? It's 108. It's just a little bit longer than this, which makes sense because the angle is really small, right? This angle is really small. So it makes sense that it's just a little bit longer than the 106.18, and the direction also makes sense. It's just a little bit south of west, which, based on our original drawing, it makes sense. So this is always the process for these kind of questions. Any vector that's not sort of at a right angle, like north, south, east, west, you got to break it down into its components, and then all you got to do is add up all the x components and add up all the y components to come up with your final triangle. Once you have your final triangle, you have the components of your final triangle, you can just use that to find the resultant, the hypotenuse, essentially. So let's try the next one. Same idea. If you want, you can try this one yourself, but what I'm going to do is I'm going to show you some ways to sort of keep us nice and organized when we're doing problems like this. So first of all, it's always a good idea to start with a sketch. So this is Mars rover is, rolling along on Mars. And we start off with 300 meters west 25 degrees south as our first displacement. So west 25 degrees south is going to look something like that, right? And that's 300 meters. And then straight west, 250 meters, so something like that. And then north 10 degrees west. So we're starting, look at this. Careful, because we're starting by going north and then 10 degrees west from there. So something like that. And that is 100 meters. I didn't really draw that too much to scale. That 100 is almost as long. I'm going to shorten that a little bit because we know it's going to be a little bit less. It's going to be a third of the length of that 300 meters. So just to keep it roughly to scale, that's what it's going to look like. So we're looking for a displacement that sort of goes in that direction. So the displacement looks like it's going pretty much west, right? The angle might be smaller depending on how accurate we sketched it. It's going to be something like that. So that's what we would expect. So in order to keep ourselves organized when we have more than two vectors, it's important to keep organized because there's going to be a lot of little calculations here. So I like to do the same thing I did in the previous question. Let's look at each of those vectors separately first, just to make sure that we're not going to make any mistakes. So the first vector, we'll call that delta D1, looks like this, right? And it's west 25 degrees south. So the angle we're given is this 25 degrees, right? And our x and our y components are going to look like that and like that, right? And we know the length of that is 300. The second one we're going to see, it's just straight up 250 meters west. That one's very straightforward. It's only got an x component of 250 meters, right? And the third one, 100 meters north, 10 degrees west. So here the 10 degrees is right there, right? Because it's north 10 degrees west. But remember what I said. We always want to take the distance from, we want to take the angle from the east or west, right? Just to make our calculations easier, because we want to find this x component first and then this y component that gets us there. And the angle that's inside that triangle is this angle here, which if the small angle is 10 degrees, this one's got to be 80 degrees. I know that's really small. Let me actually, let me zoom in and let me redraw that a little bit clearer. So the total arrow is like that, where this was 10 degrees. But we don't want that. We want the angle not from north and south, because we want to find this component and this component, right? And we like to start with the x. So we want to find this angle in here, which is 80 degrees. That's going to make sure that our x component is still cos and our y component is still sine, right? It's going to make everything nice and easy for us. So this is the way I like to do the calculation, just to make it super easy. I've got those three things there, and we can say that our total displacement, our delta dt, we didn't actually label that on our thing, we should, delta dt, right? Our delta dt is equal to the components of this vector, and the components of the first vector, we know it's going to be, so this is the x component, right? It's going to be cosine 25. So it's going to be 300 cosine 25. And the other thing to keep in mind is it's going to be negative, right? Because it's to the left or to the west. So I'm just going to write in here is the component as negative 300 cos 25. The y component it goes down, so it's also negative, and it's negative 300 sine 25. Okay? So that's our first x and our y component. Our second x and our y component, we're going to add that to this. And the x and y component of the second vector is just 250 meters to the left, or negative 250. The y component is 0. For our third displacement, it has an x component of, again, it's to the left, so it's going to be negative, what's the length of that? 100 meters. I should label that on here. 100 meters. So it's going to be negative 100 meters cos 80, right? Because 80 is the angle from the west. And the y component is going to be, it's positive because it goes up, right? So it's just going to be 100 sine 80. So the reason why I wrote it out like this is because you don't need to actually calculate these all individually. You don't need to calculate this number separate from this number. So find the number and then add up all those sums at the end. What happens if you do that is you end up with a lot of rounding error because you have to round this number and you have to round this number. But if in my calculator I literally write negative 300 cos 25 plus negative 250 plus negative 100 cos 80, so just write out this whole top part in my calculator at once, the answer that it spits out at me is going to be exact. Well, more exact, right? It's not going to have any rounding error because you did it all in one step. Same thing for the y component, all in one step. You just got to be careful to make sure that you got your negatives in the right place. And that's why I always draw the three vectors separately to make sure that anything going to the left, you can do a quick check, anything going to the left has to be negative. So all three of these should be negative. Anything going down should be negative. So this is down, it's negative. This one's up, it's positive. Okay, so let's just plug that into the calculator. Negative 300, I'll do it real time here. Cos 25 minus 250, or plus negative 250, it doesn't matter, minus 100 cos 80. And it gives me that our x component, our final x component is, oops, got to get my pen out, is negative 539. And we'll do that to 0 decimals because that's what the question's given. So negative 500, actually, you know what? Because we're not at the final answer yet, let's take 2 extra, 0.26. And the y component is negative 300 sine 25 plus 0, I don't need to include that, plus 100 sine 80, which is negative 28.30. There we go. Oh, this should have an arrow over it. This is a vector. So there, I've calculated my total x and my total y components, so that gives me my final triangle, right? It has a total x component of 539.26 in this direction, and a final y component, it's negative, it goes down, of 28.3. The resultant goes like that, right? Which is sort of what we predicted based on our drawing, right? It goes a little bit down into the, mostly to the left, a little bit down, which is what we predicted. And we need to find that angle there, and we need to find the delta dt. Well, we know how to do that. We've done that a million times. So you can find delta dt by using the Pythagorean theorem, the length of it, as 28.3 squared plus 539.26 squared, square root of that whole thing, which comes out to square root of 28.3 squared plus 539.26 squared, which is 540.00. Wow, came out to almost an exact whole number, 540 kilometers, right? And the theta is the inverse tan of opposite over adjacent, which is 28.3 over 539.26, which comes out to 28.3 divided by 539.26, which is 3 degrees, 3.00 degrees. So we'll just round that to 3.0 degrees. Look at that. They come up to nice numbers. So our final answer, delta dt, is equal to 540 kilometers. And then what's the direction? Well, it's from the west, and then it goes a little bit south. So it's going to be west 3 degrees south. There we go. Again, it makes sense because if you think about it, you're going very far to the west. So it makes sense that it's 540. That's a number that makes sense. And then the angle is very small. There we go. So this sort of format to organize everything is rather nice because you're less likely to make rounding errors, and as long as you've taken those negatives into account and made sure your angles are always from the horizontal or from the x-axis, it's pretty easy because the top ones are always cos and the bottom ones are always sine, right? So just be careful with your negatives, and if you do that, you should be okay. Okay, next question. 4 forces are applied on a box. Basically, we need to calculate the acceleration of the box, including direction. Well, remember, to calculate the acceleration of the box, what do we need? You should be thinking the most important equation of all time. F net equals mass times acceleration, right? If we know the mass and the force on a box, we can find the acceleration. We know the mass of the box, 300 kilograms, and we can calculate the net force on the box. It's not obvious because you got these four forces pulling in different directions. But if we can find the total of all these forces, that's essentially what the F net is. The F net, just remember, it's just the total of all the forces. So if you look at this, we got these three forces sort of pulling down into the right. So we can probably assume the box is going to move that way. This one's not enough to like balance all those out. So it's probably going to move in that direction. But to calculate the exact force, the total force, we can use the same method, the component method, to do it. So let's do the exact same thing we did the previous question. Going to start by breaking up each of the vectors, just writing each of the vectors by itself and looking at its components. So here's the first vector, 104 east, newtons. The second one is F2 is 71 newtons south. The third one is sort of down on an angle there. It's 122 newtons. And actually, let me put the 122 on the bottom, 122 newtons, east 15 degrees south. So again, to zoom in here, we have the east, we have the south, and we have the 15 degrees is going to be in there, right? Good to make sure that we have that correct. And then F4 goes up and to the left, and that's west 60 degrees north. So again, drawing the components, west, north, and the 60 degrees goes in there. Okay, well, and the length of that is what, 157. 157 newtons. So let's write basically a formula for each of the components of these vectors. So our Ft, or let's just call it F net, because it is the net force. F net is equal to, okay, we'll start off first components of this vector. Well, it only has an x component, it's only in the x direction. It's in the positive x direction, right? Remember, we're going to assume that this is positive x, this is positive y. So we have 104 and 0. Cool. Second vector, second force. This one doesn't have any x component, right? It's just straight down, so 0. And the y component, because it's going downwards, is going to be negative 71. Then we have the next one. This is where we have to be careful with our trigonometry. The x component, right, it's going to be the 122, and because it's the x component and we're taking the angle from the horizontal, it's just going to be 122 cos 15. The y component, the red arrow points down, so that means it's going to be negative 122 sine 15. These are all degrees, obviously. And our last vector, our last force, the one that goes up and to the left, the x component goes upward, so it is going to be positive. Oh no, sorry, it goes to the left, it's going to be negative. Negative 157. And the angle from the horizontal is 60 degrees, so cos 60. And the y component goes up, right? The red arrow goes up. So that's positive 157 sine 60. Okay, so we have all the components of all our four vectors. And now we can just do the calculation. The x component comes out to, according to my calculation, 143.34. And the y comes out to negative 24.07. I guess, or 0.08 to round to 2 decimals. Those are in newtons. So there's our final vector. Now we can find the final triangle from that, right? The resultant triangle from each of those. So we have an x component of 143.34. I'll do it over here. Where's my colors? Blue for x. So 143, let me zoom in there. 143.34. Our y component goes down, 24.08, and our resultant goes down and to the right, which is what we predicted, right? Most of the forces are pulling it this way, so it makes sense that the total force is down and to the right. So now we need to find our our F net and our theta, right? So F net is just equal to the square root of the components, 143.34 squared plus 24.08 squared, which comes out to 145.35. So let's just, because the original question was rounded to the nearest whole number, let's also do that here. So 145 newtons is good. And the theta is tan inverse of opposite over adjacent, 24.08 over 143.34, which gives us 24.08 divided by 143.34. Okay, 9.5 degrees, which isn't as much as I thought it would be, but it's just the way it is. Let me just double check. Yeah, I did it right. So it's because this force is pulling it very much to the right. These forces are both pulling it very much to the right, so the angle isn't that big. It's almost pulling the box just straight to the east. So the answer is for F net equals 145 newtons, and it's east 9.5 degrees south. So there we go. We found our net force acting on the box. So all those forces combined just equals that one force of, so it's the equivalent of one force pulling it down to the right with a force of 145. The question, remember though, is asking for the acceleration. So the acceleration, we know if we rearrange Newton's second law, acceleration is just F net over mass. And we know the F net was what we just calculated, 145 newtons, east 9.5 degrees south, and the mass, what did it tell us it was? 300 kilograms, a heavy box. So if we just divide the 145 divided by 300, we get 0.48. And newtons per kilogram, we know that's the same thing as meters per second squared. There we go. And we also need our direction, which the force and the acceleration are going to be in the same direction, right? Because whatever direction the force is, that's the direction the object is going to accelerate. So there's our answer. There is our final acceleration. Makes sense that it's low because the box is very heavy, and 145 newtons of force is not that much. So it's accelerating very slow, but it is accelerating. There we go. So this one, I really want you to pause the video and try it yourself. When you unpause, the full solution is just going to come up. I'm not going to go through every step of this one because it's very similar to the previous questions. So pause the video here and give it a shot yourself. So there we go. This one only had two displacements, right? The first displacement, both of the components were positive. The second displacement, both of them are negative. And if you add them up, that's what you get for your resultant displacement. That's what the final triangle looks like. And then solving for your answer, you get 156 meters east, 38 degrees north. So now we have the last question. I'm not going to go through this one or show you the solution to it. The answer is on the page. So that's a challenge to you. We basically have four vectors. The lengths of it are right here, so you can just add those onto the diagram. The diagram is basically done for you. The angles you can read right off the graph. And yeah, assume our normal compass, north, south, east, west, right? And you can follow the same process to try to figure it out. If you get the wrong answer, don't get discouraged. Go back, make sure your positives and negatives are correct, make sure the angles you're using are correct, they're from the horizontal, and you should be okay. Good luck.